Good morning, everybody.
Good
Great
morning.
to see you all. I know a few people are still trickling in, so not a problem with that. Okay. Let's pop open this dry erase board. I'm going to start class off slightly differently than I usually do. I'm about to open up a participation question, a warm-up for the day. But I wanted to take just a quick moment and pick up where we left off last time. So last time at the end of class, we were talking about this thing called relative humidity. Oops. Relative humidity. Who can remind me, what is relative humidity?
Is it the ratio of water vapor?
Ooh, close. So it is a ratio. And on the top, we have water vapor content. What was another term we used for water vapor content?
Vapor pressure?
Vapor pressure, yes. And then so it was a ratio of vapor pressure to what?
Saturation vapor pressure.
Yes, saturation vapor pressure. And when you calculated this thing, you got your ratio of vapor pressure to saturation vapor pressure. You would take the whole thing and multiply it by 100 to convert to a percentage. So I will give you vapor pressure. I will always give you vapor pressure. But how would you find saturation vapor pressure? How would you find saturation vapor pressure? I'll give you a hint. Saturation vapor pressure is determined by temperature. What did we use last week to find saturation vapor pressure? Okay, somebody said something in chat. Let's see what they said. With a chart. Exactly. So I will give you a temperature and then a chart that you can then use to convert that temperature to a saturation vapor pressure. So that being said, I thought rather than doing a traditional participation question, I'm still not going to grade it based on if you're right or wrong, but I do want you to make an honest effort with it. What I thought I would do today is start by having you do a few of these calculations. So in the first calculation, I give you a vapor pressure of 21 millibars. So in the first case, I give you a vapor pressure of 21 millibars and a temperature of 85 degrees Fahrenheit. And then in that Google form, I also have a link to that table that you could go to. That being said, I can also post it in chat as well. So I'll post both of these in chat. There we go. Then I can copy that. As people come in, I will post it a few more times. Okay. Leave this over and take a look and see how people are doing. Okay. All right, let's take another 2 minutes. Mhm. All right, 1 more minute. Looks like people are getting them in pretty quickly. Oh, somebody needs the link again. And then as far as significant figures, I always say round up to the nearest 2 decimal places. I'm not grading this on if it's 100% correct, but yeah, the nearest 2 decimal places is usually what I do. So for example, let's say we got a number that was like 29.3942. I would just put 29.39. I'll type that in chat as well. And if you didn't do that, you're fine too. Okay, it looks like the bulk of people have responded. So let's see what the general consensus is. And then I'll do it for us, and then we can go from there. So let's see what people said. So over here. So let's see here. I got 51.1, 51.09, 51%, 51, 51.09%, 51%, 24.71, 0.51, this was the decimal version. They just didn't convert it to percentage yet. 0.51, same thing. 51.1%, 48.66, 25%, 71.43%, 24.7 with a question mark, 61, 51.095, 51.09 relative humidity. So it looks like the vast majority of you had it right around 51%, 51.1, 51.09. Well, let's do it. So let me pull back up my dry erase board real quick. So back to this. So for a temperature of 85 degrees, if we go to that table, it would give you a saturation vapor pressure of 41.1. So for a temperature of 85 degrees, you would get a saturation vapor pressure of 41.1 millibars. And once again, that's just from that table that we looked at. So 41.1 millibars. So relative humidity would equal 21 millibars divided by 41.1 millibars. And then whatever that is, multiply it by 100. The millibar units go away because you're dividing millibar by millibar, so those go away. So just 21 divided by 41.1. And this is what I got. In the decimal form, I got 0.51094,891. To convert that to a percentage, just multiply it by 100. 51.09. That's what I got. And that looks like that's what most of you got. Or most of you were right around that. So I noticed that there were a few answers that weren't quite there. So what I will always do is I will always give you a vapor pressure and a temperature. Using this table over here, I can pull it up real quick. Sorry, give me 1 second here. A bunch of other stuff popped up when I didn't want it to. Okay. Using this table over here, for a temperature of 85, let me zoom in on that a little bit. For a temperature of 85, saturation vapor pressure is 41.1. So 85 is the temperature in Fahrenheit, 29.4 is the temperature in Celsius, and then 41.1 is the saturation vapor pressure. So that is where I got that 41.1 from. Okay. So at night, or as temperature cools down, saturation vapor pressure should decrease. That means our denominator is going to get smaller. What should that do to overall relative humidity? Well, 79.6 of you, 39 of you, said that this would cause relative humidity to go up. 8 of you said go down, and 2 of you said stay the same. So once again, the bulk of you said that this would cause relative humidity to increase. And that's exactly what it would do. So basically, as temperature goes down, relative humidity should go up. And this is always true. Temperature and relative humidity are inversely related. That means they're oppositely related. As temperature goes up, relative humidity goes down. As temperature goes down, relative humidity goes up. And it's that relationship that really ends up being crucial during a normal 24-hour day. And so that's what we're going to pick up on today. We are going to pick up on that concept, the concept of what's called diurnal variation. So I've mentioned the term diurnal before. Diurnal just means daily. It just means throughout the day, how something changes throughout the day. And relative humidity has a diurnal variation because temperature has one. And it's always the exact opposite. So as temperature goes up, relative humidity goes down. As temperature goes down, relative humidity goes back up. And so this graph right here shows these two and how they relate to one another. The green line represents relative humidity. It peaks right around where temperature is at its lowest. And then relative humidity is at its lowest right as temperature peaks. So that is this beautiful relationship between temperature and relative humidity. They are oppositely related to one another. They are oppositely related to one another. Okay. So that being said,
Diurnal.
hello?
Diurnal.
Hello? Nope. So that being said, that relationship between temperature and relative humidity is opposite. When temperature goes up, that forces relative humidity to go down. When temperature goes down, that forces relative humidity to go up. And we can actually see this on a daily basis. This isn't just something that I pulled out of a textbook or some fancy problem that I had you do. We can actually see this on a daily basis by simply looking at weather observations. So this is just some data that I took from San Jose International Airport. They have a weather station there. This left graph, the red line actually represents air temperature. And we'll talk about this green line in a moment, but just know that the red line represents air temperature. And then on this graph over here, the green line represents relative humidity. And if you notice, they are almost exactly mirror images of each other. This graph over here, this relative humidity graph over here, is almost the temperature graph perfectly flipped. It's almost perfectly flipped. Now let me take a second and talk about this other little graph down here, this other set right here, this other line. This other line represents what's called dew point temperature. Dew point temperature is the temperature that air needs to cool to in order to become saturated. It's actually a really good indicator of how much moisture is in the air. If you pull out your weather app, let me pull out mine for a second. Sometimes they give it to you, sometimes they don't. But it is actually the most commonly used weather variable for humidity other than relative humidity. No, it's not on here. Darn, I'm disappointed that they don't give dew point. But if you notice, this line is not very wavy. It's got a little bit of bumps to it, but it's really not that big of a variation. What that means is that dew point temperature doesn't really change much. And that means the amount of moisture in the air doesn't really change much. So really this big seesaw motion for relative humidity is simply caused by changes in temperature. Simply caused by changes in temperature. Ah, Jerome, good observation. Yes. So if you look on this graph over here, whenever the red line and this green line down here touch, that is when temperature and dew point are the same. There you would get condensation happening. That's actually when you would get fog. Now, sometimes the temperature on the ground, remember this isn't on the ground. Sometimes the temperature on the ground is a little bit cooler. So you can even get dew forming on the ground when the temperature is a little bit above saturation level. But great question. This is very unique compared to the other humidity measurements. So last week, I very briefly talked about 3 other types of humidities. I talked about absolute humidity, specific humidity, and water vapor mixing ratio. Those 3 humidity variables are only a function of moisture content, meaning they only change when moisture content changes. They only change when moisture content changes. They only change when you add or remove moisture from the atmosphere. Otherwise, they don't change. Otherwise, they don't change. Now, how do we actually measure relative humidity? Suppose you're a firefighter right now, and obviously right now there's a lot of fires going on. One of the things that firefighters need to be able to do is they actually need to be able to find out what the humidity where they're at is, because that greatly influences how they're going to fight the fire. Now, that being said, if you're in some place where you don't really have cell reception, you can't just look it up on your phone. Not only that, but that's telling you the humidity at a weather station. You want the humidity right where you're located. A lot of times you'll have to measure it manually. And there's a really cool way to do it. An instrument called a Sling Psychrometer. A Sling Psychrometer kind of looks like a pair of thermometers that are attached together. One of the thermometers has a little cloth on it called a wick. The other one doesn't. The one with the cloth on it is what we call the wet bulb. What we actually do is we take that wet bulb, we dip it in water, we pull it out. Attached to these 2 thermometers is a pivot that you can then use to swing it around, just kind of like what you would do for like a little, gosh, what are those things called? You swing them around like for, like a party, like, woohoo, I don't know what those things are called. But it's one of those where you just kind of swing it around and swing it around and swing it around. Now, as it's swinging around, air is flowing through that wick. That causes the moisture in that wick to begin to evaporate. Well, who can remind me from last week, what does evaporation do to the atmosphere? What does evaporation do to the atmosphere? All right, a few people have said things in chat. Yes, it cools the atmosphere. Evaporation cools the atmosphere. That's why our bodies sweat. That's why sweat cools our bodies. Because the sweat on our bodies evaporates and that cools it. So what that does is that little wick that was wet is now getting dry. In the process of it getting dry, the water on that wick is evaporating and that's causing cooling. So what's happening is that the temperature of that wet bulb is decreasing. On the other hand, the temperature of the dry bulb at the other one isn't decreasing. It's staying the same because it's not wet, it's not experiencing any evaporation. Well, if the air is really, really dry, a lot of water will evaporate off of that wet bulb. That'll make the temperature way colder. On the other hand, if the temperature isn't very dry, or sorry, oh gosh, the temperatures, oh my gosh, Tuesday brain. If the humidity isn't very dry, if it's actually very moist, if the air is very humid, you won't get a lot of evaporation, and that temperature won't shrink nearly as much. Well, you can use that difference between the dry bulb temperature and the wet bulb temperature to give you a relative humidity. There's a little chart that you can look up. And in fact, many of these Sling Psychrometers actually have the chart built into them. So you can just do it right there. And that's what many firefighters are doing right now. So here's how a Sling Psychrometer actually looks like. So it looks just like this. It's a pivot with, it's a pivot with 2 thermometers attached to it. This one with the cloth wick attached to it, that is the wet bulb. This one with the exposed bulb, that is what's called the dry bulb. As you get the wet bulb wet and you swing it around, what that's actually going to do is that's going to cause the moisture on this wet bulb to evaporate. That causes the temperature to drop. And then that difference between the wet bulb and the dry bulb is what actually gets you that difference between the two, it's what's called the wet bulb depression. That wet bulb depression is what actually tells us what the relative humidity is. So that's how we calculate relative humidity. Where do they use this? Inside the fires or just outside the premise? So they won't actually use it like in the fire, but as they're heading towards the fire to fight the fire, they want to know how the conditions are like ahead of the fire, but before the fire gets to them, so they know how to best fight the fire. So they do it as they're approaching the fire. That's a great question. So yeah, so just outside of the perimeter of the fire. Great question. Now, that's not the only instrument that can be used to measure relative humidity. If you've ever had a bad hair day before, like me circa 2006, you would know that hair is actually very sensitive to changes in humidity. Basically what happens is humidity causes hair to either expand or contract. That's what gives it its curliness, its sort of weird shape. Well, old hygrometers, these are old tools, old instruments that were used to measure relative humidity, consisted of a lot of strands of either horse or human hair that are sensitive to changes in relative humidity, and they were stretched out. And then what would happen is, as the humidity changed, they would either expand further out or they would shrink and contract closer in. That would cause a little needle on the end of this whole thing to move up or down, and attached to that needle was a drum that was rotating around, or that is rotating around. And so that could actually take a record of humidity and how it's changed over time. So that's another instrument that we've used to measure relative humidity. And then finally, the last big variable that I need to talk about, dew point temperature. So, as I've mentioned, as air temperature cools down, relative humidity goes up. As air temperature cools down, relative humidity goes up. That being said, there is a temperature that air would eventually reach saturation at. As the air temperature cools and cools and cools, relative humidity keeps going up, 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 and up. Eventually, the temperature is going to reach a level where relative humidity is 100%. That is where the air is saturated. And that is the dew point temperature. So the dew point temperature is the temperature the air would need to be cooled to in order for saturation to occur. And this is assuming no change in air pressure or moisture content. This is assuming you're at sea level, that a lot hasn't changed. But dew point temperature has one other positive to it. It's actually a very good indicator of how much water vapor is actually in the atmosphere. I'll say that again. Dew point temperature can actually tell us a lot about how much moisture is in the atmosphere. When dew point temperature is high, that means that there's a lot of moisture in the atmosphere. When dew point temperature is low, that means that there are low amounts of moisture in the atmosphere. So when dew point temperature is high, that means that the air is very saturated. You don't really need to cool it much to get saturation. When dew point temperature is low, that means that there's not as much moisture. So in order to achieve saturation, you would have to cool your air down quite a bit. You would have to cool your air down quite a bit. Now, one thing I really need to say about dew point temperature, and this is worth writing down in your notebook and double underlining it, getting it tattooed on your body, sending smoke signals to your neighbors about it, and that is dew point temperature is not air temperature. Those two are always confused for each other. Dew point temperature is not air temperature. Dew point temperature is the temperature that the air would need to be in order to be saturated. But dew point temperature is not air temperature. Instead, it's the temperature that air needs to be cooled to in order for it to become saturated. Yep, kind of like melting and boiling points, almost. The only difference is that the dew point temperature does change. If you add more moisture to the atmosphere, dew point temperature will go up. If you take away moisture from the atmosphere, dew point temperature will go down. So a high dew point temperature means there's a lot of moisture in the atmosphere. A low dew point temperature means there's not a lot of moisture in the atmosphere. That being said, this is the thing that meteorologists geek out about. So, the past few days it's been very warm and very dry, and unfortunately that's caused some fires. There was one day back when I was actually on campus at San Jose State before all this COVID stuff, where my office mate Henry Bartholomew, another Met 10 and Met 12 teacher, ran into my office and said, "Dude, have you seen the dew points? They dropped 40 degrees in the last hour." And we're all geeking out about it. The reason why that's so significant is because at that point, the air had suddenly become much, much drier. And that caused the dew point temperature to drop. So if you're ever touching anything and getting a shock from it, if you're ever feeling like your skin is very dry and patchy, look at what the dew point temperature is, and chances are it's probably very low. On the other hand, if it's foggy outside, or if it's raining, take a look at the dew point temperature, and it's probably very close to the actual air temperature because there's a lot of moisture in the air. That being said, dew point temperature doesn't change unless we add or remove moisture from the air. So unlike relative humidity, which has that very clear relationship with temperature, that diurnal relationship, that daily relationship, dew point temperature doesn't have that. Dew point temperature is only affected by how much moisture is in the air. So if we go back to that one graphic that I showed you earlier, here was dew point temperature on that graphic. That was that green line. And if you notice, the green line didn't really change much. It changed a little bit, especially in the later part of this time period. but it didn't really change much. It really kind of stayed between 52 and 56 degrees Fahrenheit. So there was a tiny bit of variation in moisture, but for the most part, dew point temperature didn't really change. So this crazy seesawing that relative humidity went through was solely caused by changes in temperature, not really by changes in moisture content. There might be some effect, but it was very, very slight. Okay, so these last two graphics I'm going to show you before I ask a very important question show you the average dew point temperatures across the United States for winter and summer. So here's winter. Based on our dew point, based on what we know about dew point temperatures, where in the United States is there more moisture? Like, where is the moisture content highest? Where's the most humid? According to this graphic.
Florida.
To the break of dawn. I'm going to Miami. Yep. Great. I just sung a Will Smith song. Yeah, down by Florida, southern Florida, down by Miami. If you notice down here, we have dew points in the 60s. That's actually very high. That's a lot of moisture. That's why even in the winter time, it's humid down near Miami. And in fact, most of Florida is very humid. Okay, where's the driest place? The place with the lowest amount of humidity on this map. A few people are mentioning the major city of Fargo in North Dakota. So that area right there, North Dakota and Minnesota. Yeah, in fact, the dew point temperature is so low that it's actually in the negatives there. And yes, you can get negative dew point temperatures. That doesn't mean that there's negative moisture. It just means that the temperature is that cold, or that the dew point temperature, the air is so dry that the dew point temperature is that low. Now let's make a hypothesis really quickly. How would you expect dew point temperatures to change from winter to summer? What would you expect dew point temperatures to be in the summertime? Are they going to be higher or lower? For those of you who are looking at the slides, don't look ahead. That just takes away the fun. Interesting. So I kind of have a 50% vote right here. I have 2 people saying higher, 2 people saying lower. So we know air temperatures are going to go up in the summertime, right? That's pretty obvious. Air temperatures are going to go up. What is that going to do to the amount of evaporation? Higher air temperatures are going to do what to evaporation? One person. It's going to increase the amount of evaporation. Well, if more moisture is evaporating, that means there's now more moisture in the atmosphere. When moisture evaporates, it goes into the atmosphere. As a result, higher temperatures mean more evaporation. More evaporation eventually leads to more moisture. And believe it or not, dew point temperatures are much higher in the summertime. This is one of the reasons why pretty much everywhere east of the Rocky Mountains, ooh, sorry everybody. Let me undo that. Thank you. Yeah, sorry about that. Okay, let me close this real quick. Oh, boy, I can't. Oh, I know what to do. Here we go. There we go. Yeah, there we go. So pretty much everywhere east of this line gets thunderstorms almost every day. These are very poorly drawn. And it's because there's just so much moisture. Make that look more like a lightning bolt. It's because there's just so much moisture over there. And a big part of it is that during the summertime, a lot of moist air from the Gulf of Mexico also works its way up. Where's the driest place in the United States during the summertime, based on this graphic? Where is the driest place? Yeah. Reno. In fact, pretty much all of Nevada. If you notice, in all of Nevada, pretty much, like that big desert, like the dry desert of the United States, that's the driest place in the United States. Pretty much everywhere east of the Rocky Mountains is getting a lot of moisture. A little bit on the West Coast, but still not a whole lot. So yeah, Fargo's not nearly as dry in the summertime as it is in the wintertime, and neither is much of the East Coast. Now I'm going to begin switching over from talking about humidity to actually beginning to talk about clouds. And then next time I'm going to talk about precipitation. So, eventually as temperatures decline or moisture content goes up, the rate of condensation becomes higher and higher and higher. If temperature cools to the dew point, condensation begins to happen. Now, an interesting fact about condensation is that water vapor molecules do not spontaneously condense. That means that they don't just automatically, boom, stick to a, or they don't just automatically transform into a liquid. Instead, they actually need something to stick to. In order for condensation to happen, water molecules need to stick to some kind of non-water product or non-water particle. We like to call these hygroscopic. Basically, a hygroscopic molecule is something that seeks water. So it goes on Tinder, it looks for water. If it sees water, it swipes right. That is what hygroscopic basically means. It means attracted to water, seeking water, wanting water, thirsty for water. I guess in more ways than one. And these non-water particles, these non-water things are what we call condensation nuclei. And believe it or not, at the center of every single water droplet is a condensation nuclei. It's a little non-water particle that water sticks to. And then what happens is, if enough of these little water molecules stick to that particle, the particle or the amount of water that's amassed can become big enough to become a droplet. Now, what's crazy is that in order for it to go from a droplet to a full-blown raindrop, you actually have to undergo a different process. We'll talk about that next time when we start talking about precipitation. But for right now, just know that in order for condensation to be efficient, in order for condensation to really happen, water molecules need to stick to something that isn't water. We call that something a condensation nuclei. And if enough molecules stick to that nuclei, then the bead of water grows enough to become a droplet. Okay, Terrence, that's all well and good, but what are these condensation nuclei? Kind of sounds weird to think that there's some non-water thing, a grain of salt or a speck of dust or something like that at the center of a water droplet. Well, believe it or not, the air that you're breathing right now is rich with these things. As a matter of fact, here near the surface of the Earth, in very, very, very clean air, air that none of us have been lucky enough to breathe, there are about 10,000 condensation nuclei in every cubic centimeter of air. It's about the size of your pinky tip. So about the size of your pinky tip, that's about a cubic centimeter. There are still about 10,000 condensation nuclei in just that tiny little area, and that's in very clean air. That's in very clean air. And some of the things that make up this condensation nuclei include smoke. And in fact, every so often, some of these fires can actually trigger what are called pyrocumulus clouds. Because all of that smoke, once it gets into a place where there's enough water, it'll actually begin to form a cloud. Sea salt, so over the ocean, a lot of the clouds that you see over the ocean form because of sea salts. Those are little salts that whenever a wave crashes, some of the salt ends up getting sprayed into the ocean or into the atmosphere. And that can act as condensation nuclei. Dust can act as condensation nuclei, so any kind of dirt, dust, anything that gets kicked up from the ground. And then, believe it or not, bacteria. Yes, when you get hit by a raindrop, many, many times at the center of that raindrop are actually little cells of bacteria. Now, are they harmful? No. They're basically just part of nature's ecosystem getting a free ride from one place to another. But just kind of a cool thing to think about. So as air temperature cools down, as air becomes more saturated, we begin to see more condensation. All these little particles of dust or sea salt or bacteria act as excellent condensation nuclei, and those allow cloud droplets to grow and eventually form full-blown clouds. On the surface of the Earth, those condensation nuclei aren't as necessary because near the surface of the Earth, there's solid things that water droplets can stick to. And that's how dew forms. At night, the temperatures right near the ground get much, much colder than the temperature 1.5 to 2 meters above the ground. So at that eye level that we normally measure temperature, at night, the temperature near the ground is much colder. Don't believe me? Even on one of these hot days, go outside at night and go for a walk. And go for a walk barefoot. And your feet will be cold, even during the summertime, because that air right near the ground cools down due to radiational cooling. This is especially common on clear, cool nights with calm winds. And the reason why is because it's these kind of nights that are clear, that are calm, that are cool, that air temperature decreases rapidly. And when that happens, you get dew sticking to things. One other interesting thing is that in the wintertime, even here in the Bay Area, in the wintertime, sometimes the temperature outside will get cold enough to where the air right near the ground is actually below freezing. Dew will still form, but instead it actually forms as ice instead of water droplets. And we call that frost. Have any of you ever had frost on your windshield or frost on the grass when you were stepping out? Has anybody seen that before? Oh yeah. I've seen it here in the Bay Area. There have been times where walking on campus in the morning, so if I'm on campus in the morning and I'm walking around and I take a look and I notice that blades of grass kind of have this like almost glaze-like on them, this white glaze-ish kind of thing, and that's actually frost. So that's actually frost. Or if you've ever had frost on your windshield before and you have to scrape it off, That happens too a few times during the winter time. Frost can actually be pretty beautiful. Sometimes it gives you like that nice white, icy kind of look to it. Like I said, few times when I've actually walked from my dorm to the classroom, or back when I was a student, I would do that. I would walk from Washburn Hall, where I was staying at, to my office at in Duncan Hall at San Jose State. And I would, right outside, there were some bushes, and I noticed one day that they were covered in frost and kind of loved it and geeked out about it. Now, frost isn't as common here in the Bay Area, but there's something that is much, much, much more common here in the Bay Area. And so this goes into lesson 11. If you actually go to Canvas and you open up lesson 11, I have to ask you all a very important question. WTF, or what the fog? Okay, I know that was a groaner, but fog is very common here in the Bay Area, right? If you've ever been to San Francisco in the summertime, foggy, foggy, foggy. This is actually a picture that I took. I was actually coming back from Colorado on the train. Like I've told you before, I love taking the train. I was actually taking the train back from Colorado. And as we were pulling into Emeryville Station in Oakland, right across the way, I saw this thick layer of fog, and sticking out of it were these two little pillars. That was actually the Golden Gate Bridge. So the entire bridge was pretty much covered with this thick fog, except for the very tops. And then once you got above that, it was a beautiful, clear day. So how does fog form? Well, there's actually three types of fog: radiation fog, advection fog, and upslope fog. And each one of them forms in a different way. But believe it or not, each one has a place in California where it's very common. In fact, each one has a place not that far away from here where it's very common. So let's talk about each of these very, very briefly. Radiation fog, commonly known as ground fog. So it's commonly known as ground fog. And the reason why it's called ground fog is that it forms when air near the ground cools rapidly due to radiational cooling. So at night, there's no sunlight coming in, but the ground is still giving off heat. Why? Because it has a temperature above absolute zero. As it's giving off heat, it's cooling down. Eventually, it can cool to saturation, and boom, fog forms. If you've ever driven by a park at night and you looked at the park and it kind of looked murky and foggy over the park, that's what has happened there. The only difference is that the park also has a lot of plants. Those plants are exhaling a lot of water molecules, and so that makes the air even more saturated. But what happens is the ground cools down really quickly. And so you get this situation where the ground is really cool, the temperature a few feet above the ground not as cool. So you end up having warm air on top of cold air. Does anybody remember what that's called when you have warm air on top of cold air? I've mentioned it like once or twice in this class. Starts with the letter I. It's also on the slide. An inversion. Yes, an inversion forms. So you get warm air on top of cold air. That warm air actually behaves like a lid, keeping the cold air trapped below it. So you get warm air on top of cold air. The cold air gets trapped below the warm air. And so all of that fog gets trapped down there. During fall and winter, this layer of fog can actually become very thick and very dense. And it's especially common in valleys, where valley floors can actually get really cold at night because cold air from hillsides roll down into the valley, making the valley even colder. So you can get a lot of radiation fog at night in valleys. So that being said, what is the biggest valley in California? The biggest valley in California. The one that's known for all of its farming, also known for the I-5 to get you from here to LA. The Central Valley. Yeah. The Central Valley actually gets this fog very commonly in fall and winter time. They actually have a name for it. They call it Tule fog, or T-U-L-E fog. So they call it Tule fog, and sometimes this fog can actually stay in place for days, unless something changes about the upper atmosphere. Either winds blow in, or cold air pushes that warm air away and allows for the air to mix out. That lid essentially gets taken off. And so this can actually stay in place for days. And some days it can get very, very dense. I'll show you an example in a few minutes. So here is the Central Valley of California, the entire Central Valley, which consists of all of California's big top tourist attractions, including Bakersfield there, Fresno right there, the beautiful city of Stockton right there. I think Modesto's somewhere here. So all of California's top tourist attractions, not really, but all of California's farms. But look at how thick and dense that fog is. It's just trapped there in the Central Valley. And it can actually hang out for a long period of time. It can hang out for a long period of time. And in fact, if you give me a second, let me show you how bad it can get. Here is how bad it can get. Let me pull up an image here on ye olde Google. Okay. Here we go. Here's one. So let me share my screen over here real quick. So that's one example of Tule fog right there. So let's see here. Oh, this is the National Weather Service San Joaquin Valley Hanford Station. An old roommate of mine works there. But it can get pretty dense. And in fact, here's another example of Tule fog just covering all of the Central Valley. So it can actually become pretty dense. And in fact, in some cases, it is so dense that they actually urge people to stay home. I know it kind of sounds weird now with COVID forcing us all to stay home, but in non-COVID times, schools would actually have fog days. Very similar to how parts of the United States have snow days where it's just too snowy to go out. They would actually have fog days, days where, hey, it's too dangerous to drive in this, you stay home. So that's how thick it could get. Now, that's common in the California Central Valley. But what about us here in the San Francisco Bay Area? Yeah, we do. Unfortunately, we have smoke days now. Well, the kind of fog we get here is what is called advection fog. So I don't know if you remember the term advection. Advection is basically the horizontal transfer of heat. Well, what happens is that warm air will blow over cool waters. Those cool waters have very saturated air associated with them. And when you get warm air blowing over them, that warm air cools very quickly to saturation and fog forms. This is the exact same thing that happens when you go out for a pint of beer or for a glass of iced tea or for a soda or for anything, and they hand you a glass of water or a glass of beer or a glass of whatever, and it looks like the outside is sweating. The outside of the glass is sweating. Have any of you experienced that before? Condensation on the outside of a glass? Well, the same thing is happening. Basically, the air outside of that glass is much warmer and much more humid than the glass itself. When that warm air comes into contact with the cold glass, it causes the air to rapidly cool, and then boom, condensation occurs. This is what we get here in San Francisco. This is the kind of fog that forms in San Francisco, advection fog. So what happens is every single day, the air offshore is a little bit warmer than the waters are. That warmer air blows over the ocean waters, where it then cools down rapidly and fog develops. And then that fog then hugs the shoreline. Pretty much the entire California coast, at least from Santa Barbara all the way up to Oregon, is usually packed with advection fog. So if you've ever driven along PCH, especially in the summertime, if you've ever driven along PCH from, or parts of Highway 101, from Santa Barbara through San Luis Obispo, through Pismo Beach, up into Cambria, then Big Sur, then Monterey, then Santa Cruz. Santa Cruz actually kind of gets a little break from it. But pretty much that whole area is oftentimes socked in with fog. And sometimes the fog can be so heavy, it can even rain. You can even get rain that falls out of the fog. Well, here's the crazy thing. Here in California, especially, our geography actually adds an additional wrench into this. So along the California coastline, there's a cold ocean current called the California Current. The California Current actually brings cooler waters from north of us, from near Alaska, down along the California coastline, and down into Southern California. So if you've ever gone swimming at our beaches, you know they're cold, right? They're cold. So that gives us cold water. But actually, the geography of the California coastline allows for an additional phenomenon to occur called upwelling. Believe it or not, our ocean waters just off our coast are actually colder than the ocean waters off the coast of Oregon, Washington, and even southern British Columbia in Canada. Our ocean waters are colder than theirs. So why is that? Well, it's because of what's called coastal upwelling. And here's how coastal upwelling works. So during the summertime, there's this big high pressure off our coast called the Pacific high pressure. Whoops, I'll go back up to that because I'm going to draw all over this. So actually, let me plop in a big H first. So up here, we have this big high pressure system. So we have this big high pressure system. Let's see if I can make that bigger. I don't think I can. Oh well. We have this big high pressure system. What that actually does is that actually forces air to travel from north to south along the California coastline. Well, the shape of our coastline makes it so that these winds blow almost perfectly parallel to the coastline. Almost perfectly parallel. And what that does is that when you have winds that are blowing perfectly parallel to a coastline, they almost kind of skim into the water and they force that very, very top layer of water offshore. So warmer surface waters are actually forced offshore. And then you end up getting this empty area. Well, something's got to fill that empty area. What actually fills it is colder water from below actually comes up and takes its place. So basically what happens is as the winds are blowing parallel to the California coastline, they're pushing water offshore. The whole phenomenon that causes it is this thing called Ekman transport. Ekman transport. A little beyond the scope of our class. When I teach oceanography, I go in depth into Ekman transport. But basically the end result is that these winds force water offshore. Cold water from below rises up to take its place. And that's what upwelling is. So that's how upwelling works. Basically, cold water from below comes up to take its place. So let me show you the consequence of this because it is actually pretty fascinating, at least in my opinion. Here we go. So the consequence of this, as the winds are blowing parallel to the California coastline, as they force warmer surface waters offshore, colder waters rise up to take their place. What this actually means is that the waters right off the California coastline are much, much colder than the waters a few miles off the coastline. And in fact, the end result is this right here. The average summertime ocean temperatures off of places such as Cape Mendocino, Fort Bragg, which is right here, Eureka's up here, San Francisco is down here Santa Cruz, and then Monterey. The ocean temperatures here are colder than they are near Seattle, Portland, the Oregon and Washington, and then even Canadian coastlines, where the ocean temperatures can oftentimes be closer to the 60s, mid 60s even. So believe it or not, the beach weather up here is better than it is down here. Well, the consequence of this is that you have cold water right near the ocean, right near the coastline, warmer water further offshore. Warmer water leads to warmer air. So you end up getting a nice big patch of warm air. Which then blows on shore. And just like as the hot air touches that cold cup, that cold glass of ice water that you're drinking, as this air travels over the cold water, boom, it condenses into fog. And so that's why fog is so common along our coastline. Because not only do we have these cold waters, but we also have this upwelling phenomenon. And this creates some pretty interesting consequences. One of the biggest consequences, sorry, give me 1 second here. One of the biggest consequences is that common San Francisco fog. Yeah, San Francisco is very foggy in the summertime. I mean, there will be a few times a year where we get a nice offshore flow, nice offshore flow that keeps San Francisco warm. But for the most part, in the summertime, if you go into the city, it is cold, it is foggy, people are wearing coats and boots, and they're doing all of that because It's so cold and foggy. And what does this mean for Giants fans? For San Francisco, people who live in San Francisco? Well, an interesting consequence to this is that the months of September and October are actually warmer on average in San Francisco than the months of July and August. So September and October are San Francisco's warmest months. In much of the rest of the United States, July and August are the warmest months. But for San Francisco, it's September and October. So it's a pretty interesting consequence of coastal upwelling and of advection fog to San Francisco's climate. In fact, I have a friend who lives in San Francisco, and last week when I was asking people what their favorite thing was about fall, she said, I live in San Francisco. This is our summer. And yeah, very true. But this also inspired a very famous quote that is oftentimes attributed to Mark Twain, which was, "The coldest winter I've ever spent was a summer in San Francisco." The coldest winter I've ever spent was a summer in San Francisco. Last type of fog I'm going to talk about. This one, it doesn't take nearly as long as the other ones. This is very common in California's mountain ranges. So even the Santa Cruz mountain range will actually get this very often. It's what is called upslope fog. The way upslope fog works is that you have air that blows on shore, and that air is usually moist. Once it hits a mountainside, it can't go through the mountain. No, it has to go up and over the mountain. And as it goes up and over the mountain, it expands, it cools, my corny dance, and it condenses. So the air expands, it cools, and it condenses. And so fog is very, very common. Very, very common on mountainsides. So the Santa Cruz Mountains, over by where Santa Cruz is, they get a lot of upslope fog. The Sierra Nevada gets a lot of upslope fog. Some of our coastal ranges get a lot of upslope fog. Otherwise, there wouldn't be any fog there. But because that moist air is forced up and over the mountain, that causes fog to form. So basically what happens is moist air approaches the mountainside. Once it hits the mountainside, it has to go up. As it goes up, it expands, cools, and condenses, and boom, you get fog. And so that is how you get fog in that case. So just to review really quickly, there are three types of fog. There's radiation fog. That's common in the Central Valley of California. There is advection fog. That's common in San Francisco, as well as the whole California coastline. And then there's upslope fog. That's common in California's mountains. But all three of these things put together show that California can be a pretty foggy place. On top of smoky and dry and all the other stuff, we get a lot of fog. And what's actually really cool is that this upslope fog is why we have all of these green trees in the Santa Cruz Mountains. Those trees actually feed off of that upslope fog. So kind of a cool fact to know about. And that's pretty much it for today's lecture. Just one thing I'll say before I wrap up. So our next quiz is on Thursday. I have already posted the study guide for it, so that's already up. It's just like the last quiz. I will let you go about 10 minutes early, 15 minutes early, and you will have until Friday night to do that quiz. All right. Another thing, homework number 2 is also due on Thursday night. And I've also just opened homework number 3. In homework number 3, you get to look at clouds. All right, so that's everything for today. If you have any questions, comments, concerns, I can hang out for a few minutes. Otherwise, It shouldn't be as warm today, so enjoy it. It's going to get warm again tomorrow, so enjoy that, and I'll see you all on Thursday. So long, everybody.
Have a nice day.
Have a nice day.
Nice day.
Bye. Oh, no, you don't have to take it during class on Thursday. I will actually open it up. Somebody private messaged me. I'll actually open it up, and you'll be able to see it. You'll be able to take it anytime from when I dismiss class on Thursday to Friday, till 11:59 p.m. on Friday. I hope that makes sense.
Professor,
Yeah, what's up?
so I'm a little concerned about homework 3 because the weather near where I am, it doesn't vary greatly. So I'm concerned that there'll be plenty of days where I don't get to see like a single cloud in the sky, and so I won't be able to like take a photo.
Okay. Well, let's see how the weather changes over the next 2 weeks. Where do you live?
Near San Jose.
Oh, we'll
Right.
get in the next 2 weeks. I think we'll see some clouds roll in.
Right now the sky is just, there's a thick hazy like smoky sky with no clouds in the sky at all.
Yeah, right. No, today is not a good day. But one of the things I will do, if I do see in the next few weeks that we do have like a really good day for clouds, I'll actually post something on Canvas and say, hey, if you're looking for clouds, today's the day to do it. And all you need to do is just take a few pictures and then describe them.
Okay. All right, thank you.
And then if we end up not having any clouds, I will extend the assignment.
Okay, thank you.
Yeah, I'm not going to leave you hanging. All right? Bye. Still see a few people in the room. If you have any questions, I can hang out. Otherwise, have an awesome day and try to stay cool. Okay. Alrighty, well, if you don't have any questions, I am going to shut it down, and I will see you all later. Bye.